It's preparing. I don't have confirmation yet. The meeting is being streamed. Okay, great. Got it. So we're good. I'll share my screen and get the video started, and that should get us on the way. It's like if you're able to check the group, please, that would be helpful.
Yes, I'm on
We're live.
So PhET is a collection of over 100 interactive simulations for teaching and learning science. They're all free on the web. You can run them online or you can download them to your computer. We have simulations in physics and chemistry and a growing number in earth science, biology, and math. One of the main goals of PhET is to provide students with an open exploratory environment where they can really engage with the science content like a scientist.
I love the PhET simulations. I find that they're really fun even for me to play with.
Before it was all on a page, and now you could actually see it. You see what's going on when you connect, two wires and a battery, and you see the flow of each electron and how electrons affected by resistance, and you see everything. That's what I love about it.
One way that I use simulations is I ask clicker questions around them to really focus what students are thinking about and trying to process. Sometimes I'm using it as a demonstration, as a really effective way to describe a dynamic system to the students.
I've used Sims in homeworks. I've used the Sims in tutorials where they play basically the role of some experimental equipment.
Without having to make a mess, so I don't have to take ice and melt it and do all that, we can look, first you see it as a solid, and you see the temperature, and then you can turn it into a liquid, and you can observe the difference on a micro level that matches pretty well what they see at the macro level.
She'd show them to us in class and we'd play with them on our own, and it just gave us a chance to, see how everything worked.
One of the unique things about PhET is that it's research-based. Both in its design of the simulations, we draw from research across different areas.
They spend a lot of time testing, beta testing, and revising with students. And there's no substitute for that.
I'm very visual. I always picture the molecules bouncing around in that, and that's really how I think about what's happening in a system. So I find that PhETs match very well with the way I visualize what's happening in the system. I can show them what's in my head.
In a real circuit, they can only infer that electrons are flowing through wires by the brightness of the bulbs, but in the PhET sims, they can see the electrons.
One of the things that PhET allows that other things don't allow is when something spontaneously comes up in class and I can say, let's test it.
What happens when I put a light bulb or a battery in here? What happens when I put a pencil into this circuit?
We make the simulations highly interactive so that when students move a slider or create a different setting, they get immediate feedback as to the effect of making that change.
That is a really powerful way to learn. You learn what's important and what's not important.
We developed this saying in Physics 3, let's PhET it out. Some of us would disagree and we would well, let's just check the PhET.
Simulations allow you to go beyond what you can do in real life quickly.
Using computer simulations, we can slow down time. We can dive inside an atom.
I think PhET definitely provides real-world examples, things that in the classroom you can't see or get your hands on at all.
If we change planets or gravitational fields or time or the number of coils on a wire and see immediately what the impact of these are.
We really want to make things intuitive enough in terms of user interface so that when students sit down, they don't really need instructions in order to know how to use the simulation.
And when students use a PhET simulation, they're focused on the physics, not how do I run this simulation. That's all been made very simple.
It takes you about a minute or two to sit down and figure out all that it can do and actually start learning from it.
I've never heard a student give me negative feedback about a PhET sim.
They're a lot of fun, whether it's, shooting pianos out of cannons or doing quantum mechanics tunneling.
It gets you interested in it, and then once you're interested in it, it's really easy to learn it and just want to actually do it and explore it.
One of our main goals is to educate the world. So we give away all of our simulations for free, and we provide tools for translators across the world to translate the simulations.
The impact of the PhET applets, who right now is worldwide, which is a remarkable thing.
I think we're enabling a lot more people to learn physics and chemistry and biology in a way that will stick in their minds. And hopefully they'll have these creative visualizations in their minds that will enable them to do great things.
As a future teacher, I don't see how somebody could pass up a great tool like this.
Good afternoon, everyone. Welcome to the very first edition of the PhET Africa Share and Discuss Day, and special welcome to everyone who has joined early. We have a couple of people who are joined here, and we have a community as well within the PhET group for educators on Facebook who are also connecting with us. So we're aware and we're working with you there, and we welcome you to today's session. My name is Shola Olateju, and I am the Africa STEM specialist. I'm going to be facilitating this session today alongside a couple of my colleagues, Zach Mbasu and Diana Lopez, who are the PhET ambassador for Africa and Latin America, respectively. Zach and Diana, would you say hello to everyone in the house?
Thank you, Shola, and good evening, everyone. Thank you so much for creating the time to be here. My name is Zach Mbasu. I am the PhET Africa Ambassador. I'm based in Nairobi, and I'm really excited to be part of this share and discuss webinar series. And I'm looking forward to having great discussions. Thank you.
Hello, everybody.
Thank you, Zach.
My name is Diana. I am the PhET ambassador in Latin America. I am from Mexico, and I am so excited of this first session of Share and Discuss, a project that I expect take years and years of people sharing about PhET simulations. Thank you.
Thank you, Diana. Thank you, everyone, again for joining. We also would like to know where you're connecting from. So please, if you can write your name and the country you're connecting from in the chat, we would like to know more about you. For those joining us on Facebook, please write in the chat as well, and some of my colleagues definitely will be collecting both your questions and all of the contributions you're making. So everyone is being considered and no one is left out. We also have someone special with us who is going to be our guest speaker, is Dr. Umesh Ramnarain. I'm going to give him some time to speak a little later, and is professor in science education and head of department in science and technology education at the University of Johannesburg, South Africa. He'll be sharing about his research finding and experience on today's discussion. We're going to be discussing the use of simulation in PhET science learning. Today, as you would agree, technology is transforming every fabric and sector in our world, and technology-enhanced learning has become a key strategy both nations and institutions are increasingly leveraged to further improve and facilitate the teaching and learning process in their respective domains. But the use of virtual learning technologies such as simulations has become of great interest because because they have shown to enhance conceptual understanding of abstract concepts and also foster motivation and interest in science learning. So we also welcome Professor Umesh, and I'm going to, just before I hand control over to him, we're going to look quickly at the outline for today. We're going to look at some of the things we'll cover today. We're going to learn about PhET, of course, what PhET is about and the objective and what we're trying to do. We're also going to come to understand the effect, of course, the importance of share and discourse, and why this is very, very dear and important to us, and why, of course, they are important in this entire conversation, and also how to continue this conversation beyond the 1 hour restriction we have today. We'll then hand it over to Dr. Umesh, who's going to share from his wealth of experience. He has a couple of research already around the effective use of PhET, but also this is something he spent extensive years on in terms of personal research, especially within the African context. And we're going to allow you as well. We've saved enough time towards the end of the session for you to ask enough questions, so everyone will be able to ask. But I strongly advise that while the session is on, please, you would have the chance to ask questions towards the end, not while the session is on. So I advise that you please write your questions both in Zoom and on Facebook, irrespective of where we are joining from. Members of the team is going to be aggregating all of the questions, and we'll spend time to address them before the end of the session. So please don't wait till the end of the session. If you have questions, please write in the chat while the conversation is ongoing, and we'll put them all together and address them before the end of the session. A few people would also have the chance to speak, perhaps while the session is ongoing. But yeah, we're going to get in touch and manage that going forward. Just before, we're going to learn a bit about PhET. Of course, for those who are just learning or joining us for the first time, what is PhET? PhET was founded in 2002 by the Nobel laureate Carl Wyman. The PhET Simulation project at the University of Colorado creates free interactive math and science simulation. PhET Sim are based on extensive education research and engage students through intuitive game-like environment where students learn through exploration and discovery. They emphasize making connection between real-life phenomena and the underlying science, and help to make visual concept and of microscientific concept more accessible to students. So a lot of the things perhaps that causes cognitive load and a couple of other challenges that are an obstacle to learning science, the SIM definitely address. And today, that's some of the things we're going to be considering. The goal of the PhET project is basically to make science learning more engaging by, of course, allowing students interact and discover key ideas around some of the concepts that they're being introduced to. Also make it relevant and, of course, connect all the concepts and what they are learning to everyday life, so everything is relatable and within the context that they find themselves. We also ensure that the sims are accessible, of course, intuitive and understandable, and we also consider, of course, the learning needs. We look at making them available offline and online, and also in the language that everyone is most comfortable in. And then personalized, of course, the sim also encourage students to learn at their own pace and student agency where they can lead their learning, and the educator or teachers in this case can serve as facilitators, as against, of course, the one leading or directing the learning process. So for us, we say we make learning science more like doing science, as against the passive approach to learning. Learning with PhET Sim is active and engaging. At the moment, there are more than 190 sims, all free, and they can be run both online and offline, just like I mentioned, available in various languages in Africa and across the world. And of course, more languages are also being made available. You'll learn at the end of the session how you can also get involved if you want your language to be made available. If it's not there, how you can get involved, or just let us know how to also support that. So the Africa Share and Discuss is one of the many efforts here at PhET, and we put that under the PhET Global Initiative that seeks to improve both the access and impact of PhET simulation. And we do that through a community forum for elevating PhET use in Africa. Its goal is to increase the pedagogical effective use of PhET simulations for STEM teaching and learning. In future, and even in these sessions, the webinar series will attempt to spread research findings by African education researchers on simulation-based learning, highlight their finding and best practices to improve, of course, the practice and effectiveness of the use of STEM, but also importantly to distill it in in relatable bits that we can leave the session and find ways and opportunities to put them to practice in our classrooms immediately. And also the session seeks to facilitate connection among education stakeholders. This series will continue monthly and will run on every third Wednesday of the month. And of course, considering our time, we've looked at ensuring it comes up just after work hours and before it gets too late for everyone. So yes, the time also is going to continue to be shared. So I encourage that we all join the mailing list if you're not part of it already. And also follow us on social media so that you can receive updates as they become available. The session is definitely open to everyone, including teachers, researchers, and school owners and district leaders, where they can learn strategies to either adopt and use in their classroom, and validate its effectiveness and how to also improve it within their context, but also support educators who want to use it at scale, or multiple educators using it in their classroom. Without further ado, and without holding your breath for too long, I'm going to invite Professor Umesh Ramnarain again. At this point, his main research interest is on inquiry-based science education, with particular focus on its uptake in South African classroom, where past policies have resulted in learning contexts that are complex and diverse. Professor Ramnarain makes such complexities explicit and centrally organizing theme to his research, and he systematically addresses a number of inherent and inextricable context-dependent factors as they pertain to South Africa, but most importantly, apply in similar contexts across the world. His research has been published across many top journals, and today we have the pleasure of having him join us to share his extensive research. Thank you for joining us, Professor Umesh, and over to you.
Right, so thank you so much for the welcome and introduction. It's much appreciated. I really feel quite honored to be the first speaker in this webinar series, and very much part of the PhET community that I can see extends quite far and wide. So let me start sharing. Okay, I think you'll have to remove yours, please. Okay. All right, so the focus of my talk today, I hope you can see that, is the use of simulations in physical sciences classrooms. Let me see if I can make that bigger. Okay. All right, if that's fine, I'm just going to continue with that. So the talk today is going to look at the use of simulations in physical sciences classrooms. Now, after having used PhET simulations over quite an extended period of time as a teacher, educator, and researcher, there's much that I could say about PhET. But for today, I'm going to be focusing on the affordances of SIMS for the teaching and learning of science. I will make a number of assertions, but these are all going to be based on the research that I have conducted over the past few years with colleagues and students within the South African educational context. I will zoom in on two questions. Firstly, why PhET simulations, looking at it from a research-informed perspective. And secondly, what pedagogical approaches have worked in the studies which I have conducted. So, of course, as teachers, we all recognize that the fundamental aim of science teaching is to help students to develop an understanding of the natural world. So what this means, well, what does the word world contain, how it works, how can we explain and predict the behavior of phenomena? Now, I think it's widely accepted that the most effective way to actually do this is by means of practical work. The pivotal role of practical work is best depicted in this diagram. Most probably you have come across it maybe in your teacher education. So you can see I have the practical work connecting these two domains. On the left-hand side is the domain of objects, observables. These are things that you find in our physical world. And on the right-hand side is a domain of ideas. And the domain of ideas speaks to how we make sense, how we conceptualize this physical world. And practical work is a link which connects these two domains. So the central purpose of practical work is to enable learners at school, students at universities, to try and conceptualize and to make sense of what is happening in these natural phenomena which we have around us. Now, one of the earliest reports on practical work, I don't intend taking you through a history lesson, but the earliest report on practical work was in 1963, and it was titled Practical Work in School Science, and it focused on schools in the United Kingdom. One of the core findings of this report is that it identified some of the common challenges which are experienced in the enactment, in the practice of practical work. And these included, firstly, that the goals of practical work were somewhat diffuse and not well defined. There was a lack of laboratory facilities. Teachers are poorly trained. There's a lack of time and large classes. Now, that was in the year 1963. Okay. Now, 2 years ago, I became involved in a book project, and that the title of the book was School Science Practical Work in Africa. It was quite uncanny for me to learn from the contributions from academics, researchers, teachers across the African continent, that the challenges to practical work that were reported in 1963 are basically the same as what we are encountering today. Now, despite a strong African imperative to advanced inquiry-based science education in the classroom, this has unfortunately not translated into classroom practices. And some of the reasons, some of the factors that we can use to explain this include lack of resources, lack of proper facilities, teachers struggling to complete the curriculum and having difficulty in incorporating practical work in their teaching, teachers not confident, poorly trained teachers, and of course there's also a fear factor concerning the doing of experiments. So if one looks at 1963, I think you would accept that really not much has actually changed. We still seem to be grappling with very, very similar issues. So this actually stimulated my interest in simulations, in trying to understand what could be the role of simulations in affording learners at school, students at university, virtual hands-on experiences where they could investigate phenomena around them. The next figure I present, pretty similar to the one that I've just presented. The difference here is that connecting the two domains, we now have PhET simulations. So the way in which we see PhET simulations is it provides opportunities, experiences for learners to deepen their understanding of the natural world by asking questions, collecting data, interpreting data as evidence, communicating findings. So essentially, the way in which we regard PhET simulations is it is a tool which can be used to promote inquiry-based learning. So this is my hypothesis, which informed my research endeavor. Theoretically, it makes a whole lot of sense. And I wanted to understand, is there evidence that can actually support this hypothesis, which we have about PhET simulation? So I'm now going to be sharing with you some of the research which I have done. These are 4 studies which have been conducted in South Africa, studies which have been conducted with my students and also with my colleagues. So the first one, which I have there, looks at the impact of simulations in eradicating misconceptions in the study of current electricity. So of course, as teachers, we would come to realize and we would know that misconceptions are faulty scientific understandings which students bring to the classroom. They are quite resistant to change, and often they act as a barrier to science concept formation. These misconceptions are quite well documented, and there are numerous misconceptions in the area of electricity. So looking at this simulation, which I'm depicting over here, in this particular study, titled The Use of Simulations in Correcting Electricity Misconceptions of Grade 10 Physical Sciences Learners. This simulation was used by teachers in addressing misconceptions that were identified from a pre-test that was administered. The misconception in question here is well known globally, and it is referred to as the parallel circuit misconception. And the understanding that learners have on this arrangement in an electric circuit is that as more light bulbs are added in parallel, the brightness decreases due to an increase in resistance. So of course we know that that is incorrect, but that is what students firmly believe in. It's an intuition that they have, that as you increase the number of light bulbs in parallel, this is going to affect the brightness. And the reason for it is that they have an understanding that as you add more in parallel, the resistance is going to increase. So this was one of the misconceptions that had been...
Sorry to interrupt you, Prof.
Yes, hello.
Just a request, like to put the presentation slide in slideshow. So yeah, if you go down.
Yes, no, that's the icon you just left. The next one. Spot on, yeah.
Thank you.
Okay, wonderful, great. Sorry about that. Yeah, so this was one of the misconceptions that had been revealed. And in this investigative study, we wanted to understand what could be the role of this simulation in eradicating this misconception. So in addressing the misconception, the teacher supported learners in using the appropriate PhET simulation as is reflected here to effect conceptual change towards a scientific understanding. The teacher firstly showed the learners how to construct the two circuits as we have there, circuit X and circuit Y on the simulation, and how to place these two circuits alongside each other. Thereafter, the teacher allowed the learners to run the simulation in order to observe the brightness of the light bulbs as more light bulbs were added in parallel. The learners also took note of the voltmeter reading. We then administered a post-test to try and understand, is there any shift in their understanding? And statistical analysis of the data that was collected revealed that there was indeed quite a significant difference in performance of learners on the pre-test and on the post-test, with learners performing much better on the post-test. And this suggested to us that this intervention using the simulation did result in a conceptual change. So the question is, how can we explain this result? So we engaged with learners, conducted interviews, and tried to learn more on their experiences of using the PhET simulation. And what became evident to us is that by interacting with the simulations, the learners were able to investigate their misconceptions. That was the initial hypothesis, the initial prediction which they had. And they were able to reach a finding that contradicted what they initially thought. So in this way, in terms of using a bit of psychology here, the learners were plunged into the state of cognitive conflict, a state of uncertainty, sort of a disequilibrium, where they started to have doubts about the initial conception, which was the misconception. And when they were in the state, they were in a better position to now accept the scientific conception, and in this way, effect conceptual change and to eradicate the misconception. So this is just one example of, a common misconception that the learners have. But through the study, there were other misconceptions, and we had this very same result when we used the PhET simulation as an intervention. Okay, so I'm now going to take you to the next one. And this study here looked at the learning of chemistry, and the focus here was on attitudes. So we wanted to understand how is it that by using PhET simulations that there could be a possible change in attitude of the learners towards the learning of chemistry. So this was a mixed method study. For those of us who are not researchers, mixed method actually refers to the type of data that was collected. So we collected quantitative data that was by means of a questionnaire that we had administered. And at the same time, we also interviewed learners. So that was the qualitative data. The quantitative data was collected by means of an attitude towards chemistry questionnaire. And in this questionnaire, there were questions and items which spoke about the students' understanding or the students, the importance which the students attach towards that particular chemistry module, the difficulty, the interest, and the usefulness. The target group here was third-year Bachelor of Education students. The activities that the students were engaged in required them to manipulate the PhET simulation, to establish reactant and resultant products. So as we can see that this concerns now chemical reactions, and we looked at acid-base reactions, and to measure the degree of acidity or alkalinity in relation to the electricity that was generated by free ions. So we can see that that is quite clearly depicted in this figure here. And what we came to realize, again, administering this questionnaire as a pre and post-test instrument, is that by the students having the experiences in PhET, there was a positive shift in their attitude. So we wanted to understand more about this shift, so we conducted interviews with students. And what the students indicated to us is they felt that they had a greater sense of autonomy when they were engaging with the PhET simulations. They were more in control. They enjoyed it because of the engagement. And they also pointed towards an improved understanding as a result of the visualization which was created on these phenomena. So as we can see here, the particles, these reactions happen at very much at a submicroscopic level. So the students cannot visualize this, but by means of the PhET simulations, it improves the visualization and they come to understand better the chemical reactions, the collisions between the particles which are happening over here. They also pointed out that they were able to manipulate, they were able to change variables, and instantaneously they were able to see the effect of that. Okay, so I'm now going to move on to the third one. And this particular study again focused on pre-service teachers, Bachelor of Education students, and it compared achievement in chemistry. So we used a quasi-experimental design. So we separated out the students into two groups randomly. So the one group of students were doing experiments, hands-on traditional laboratory experiments using physical laboratories. And the other group were subjected to the PhET simulations. So here again, we administered an instrument, a chemistry instrument. The test was administered that assessed their understanding of atoms, acid-base solutions, chemical reactions, and the applications of Beer's law. We noticed for both groups, after engagement in the experiments, both the traditional and the virtual experiments, there was an improvement in their performance, in their achievement, in the post-test scores. But for the virtual laboratory intervention, there was a significantly higher achievement score compared to the students who were in the traditional laboratory group. In other words, students who did the simulations performed better. So the diagram that you see here is a screenshot of a task where students investigated the relationship between the concentration of a solution, transmittance and absorbance, and this is referred to as Beer's law. Okay, so that was the third one. The final study, which I will now share with you, involved learners at school, grade 8 learners. And the purpose of this was to investigate the effect of interactive computer simulation supported inquiry on their understanding of atoms and molecular structures. So this again focused on chemistry learning. Here the experimental group used simulations in inquiry-based learning as an intervention to enhance the understanding of atomic molecular structures. The control group used physical models, so actual physical models to build, to draw, investigate, and to manipulate the structures. And the key finding here was that the learners in the experimental group who use the PhET simulations perform better than the learners in the control group. So the PhET simulation experienced by the experimental group, as is reflected here in this diagram, is called build a molecule. For this simulation, the following goals were set by the teacher. Firstly, the learners had to describe the difference between an atom and a molecule. They had to construct simple molecules from atoms, recognize the subscript in the molecular formula, indicates the number of atoms, recognize the coefficient in front of the molecule indicates the number of molecules, and they were also required to associate common molecular names with multiple representations. So the figure that you have here is a screenshot of this particular simulation, which is called build a molecule. We also administered a questionnaire. We wanted to understand more about the experiences, and what we learned there is that the experiences were quite positive. The learners spoke quite similar as to what they encountered to what the students at the university had experienced. They spoke about the autonomy that the simulation afforded them, that they felt that they were in control, they could change things around, they could manipulate, and they also appreciate the graphics that was used in the simulation. So from these 4 studies, what is it that we can learn? How can we summarize this? So it can be summarized in the following way. I call them affordances of PhET simulation. Firstly, it enables interactivity with phenomena. Learners, students are able to manipulate things around. Autonomous learning is something else which was quite key to emerge. The learners were able to engage with the PhET simulation at their own pace. And as we know, the simulations can be downloaded. So they were able to extend what they were learning at school, and they were able to continue with that at home. It improved attitude towards science. They were more positive, and this was related to the enjoyment factor. It enabled visualization, especially when it came to chemistry learning about molecules and atoms, which we know these are representations which happen at the submicroscopic level, but due to the PhET simulation, they were able to perceive, and they were able to interact with the molecules and the atoms. Conceptualization, in other words, it supported the understanding of the science concepts. And of course, the last one, not to be taken too lightly, is that they really appreciated the gaming element to the PhET simulation. So it was fun learning for them. Now, if one looks at the pedagogical approaches that were adopted by the teachers, well, we identified certainly guided structured inquiry. So certainly the PhET simulation did encourage inquiry-based learning. And as I mentioned already, across the entire African continent, this is a very, very strong curriculum imperative, but it's not something which is translating into the classroom practices of teachers. Another approach which was used was the predict, observe, explain. And this approach was used in relation to interactive teacher demonstrations. So we did come across cases where the teacher used his or her laptop and was able to use a data projector to project it on a screen. And the teacher was able to engage the learners. So it was not just the, as we commonly refer to, the show and tell type of demonstration, but it was a more interactive demonstration. So the teacher would firstly invite learners to make a prediction. What is it that you think that's going to happen? And then through the PhET simulation, they were able to observe the phenomenon. And the final stage is where the teacher engaged the learners in discussion and trying to get them to explain what they observed, to try and conceptualize that phenomenon. So here are some of the references, and I put the links there. I think the PowerPoint presentation can be made available to our participants, but I'm also quite happy to share any of this if you drop me an email. So I think, a key question that one can maybe ask in conclusion is, can we regard simulations as a substitute for practical work, or do we consider it as a complement? And based on what I know and what I've experienced, I would say that it is a complement. I do not think it can be used as a substitute for actual practical work. I think the hybrid approach is the one which works best, where learners experience certainly the messiness of physical labs, physical practicals, and then perhaps use the simulations for efficiency, convenience, and to also save time and resources. Okay, so that is where I'm going to conclude. Thank you.
Thank you so much, Professor Ramnarain. Thank you for sharing such insight. There's so much packed in that, but we're constrained with time, so we're going to perhaps take one or two questions. Then I'll hand control over to Zach, where we can then also address some of the questions we've received from the audience. One very important point you raised earlier on while you're concluding your speech was the place of the use of virtual sim, and how the argument in terms of if that can be a substitute, or if that should replace the actual practical work. So I'm curious, what advice do you have for educators who struggle with this? And of course, I'll take that back a bit. You did mention how little change has occurred since the initial publication in the 1960s about the use of practical work on the continent, and how a lot more has to be done in that. In your opinion, what are the things you think educators have to pay attention to be able to maximize the opportunities that practical work brings? But also, which of the design elements, just some of the ones you mentioned, like implicit scaffolding, like multiple representation, do they also need to consider in the design of activities to ensure that they can meet their learning goals, but also help students retain some of the design objectives like fun, active learning, and all of the other elements that you've observed? Yes, you're still muted.
Yes, no, thank you so much for those questions. I think they're all quite insightful. So one of the things, when it comes to practical work, we try to understand why has practical work not been optimally used. And this relates to classrooms, schools, which are also well resourced. And one of the key issues there is that teachers do not properly formulate the goals, the aims that they have for practical work. I have found that to be quite, a shortcoming when it comes to the planning of practical work, because practical work has got multiple aims. Perhaps the most important one when it comes to science learning is that we see practical work as a way in which concepts, abstract concepts, can become more concrete, because learners would now have first-hand experience of investigating their ideas. But there are also other aims of practical work. We maybe also want our learners, our students, to acquire an understanding as to what is the nature of science. And that's why I say, I don't regard the PhET simulation as something which is going to replace actual practical work, because I do not think you can substitute the messiness of what happens in the lab. And through that messiness, the students come to understand that scientific activity is not a cut and dried activity, but it is very much a tentative activity, because there are so many things which are happening. There are so many variables at play, and it is almost impossible to control those variables. So that's why I very much, would posit that teachers, if they have got physical resources at school, that they use these physical resources in tandem with the PhET simulations. I think they both can be quite complementary. You spoke up the multiple representations, and that's also quite important. Teachers need to have pedagogical content knowledge. What that pedagogical content knowledge means is that teachers must have the capacity to look at abstract phenomena, abstract concepts, and they need to translate those concepts into a form, into a representation which is more accessible to the learners. And I think the PhET simulation is a great form of pedagogical representation that teachers can use, because it supports visualization. Learners can see what is happening in the phenomena. They can investigate changes. They can manipulate variables. They can engage with particles, with objects which are at very much at the submicroscopic level, which they are not able to do that in reality. So there's definitely a place. I think another issue which you also need to understand, and maybe this is in relation to inquiry-based learning, is what is the role of the teacher? Because when learners are engaged in PhET simulation, I do not believe that we should completely remove ourselves from the learning environment. I think the role of the teacher becomes even more critical when we look at these learner-centered pedagogies, and how is it that the teacher can scaffold? How is it that the teacher can facilitate the learning while the learners are engaged in the PhET simulation? So I have conducted some research in that area as well. Unfortunately, due to the time, I'm not able to share that, but I think that's an important thing that one needs to be considering. What is going to be the role of the teacher?
Thank you so much. I would just add here that this is only the start of the conversation, and I'm sure tons of people, even in the audience, have questions that we cannot extensively address today. So my first recommendation is to join the group that has been created specifically for educators in Africa, to continue to push this conversation and bring the interaction between both practitioners and researchers, to ensure that we can unearth practical ways that addresses some of the needs that are peculiar to Africa. We're going to leave the remaining time for the audience now. I'm sure some of us have questions, so please, if you're joining us on Facebook, this is a good time to write your questions. If you're joining us here on Zoom, please use the question and answer feature so it's easy to identify your questions, and we're going to address them in a bit. I'm going to hand it over to Zach now, who is going to take the questions, and we'll wrap it up shortly afterward. Thank you, Zach.
Thank you so much, Shola. Thank you, Prof, for that insightful sharing. Because of time, I'll just go straight to questions. I've identified a few questions from the chat box and the question and answer. So some of the questions are directed at Prof, and others are directed at the PhET simulation. So I'll start maybe with the ones that are directed to Prof. So the first question is about, you mentioned the challenges that exist in Africa about, teachers being poorly trained, large class sizes, and all the challenges that our classrooms experience. So if maybe we may just start with the question of accessing, for example, the PhET simulations and leading to meaningfully incorporating the simulations in our lessons, in our STEM topics. So, Prof, is this possible in our context and in our classrooms? Is there anything that we can do to take advantage of this, this evidence that the simulations help with learning of STEM topics and STEM concepts? Sorry, Prof, you're on mute.
On that. Yes, I've tried, over the years. Firstly, myself, I've been a teacher. That's how I started my career as a physical sciences teacher. And I firmly believe that we need to provide learners with practical experiences. Learning has to be hands-on. They need to be given the opportunity to investigate their own ideas. And as I said, the limiting factor has always been, the shortage of resources. Even in South Africa, which we generally consider as being, better resourced compared to the rest of the African continent, there is a very small percentage of schools which have fully fitted laboratories. So I explored other ways. The other opportunity which we can provide is the use of readily accessible, low-cost material, which much of these we find around the home as well. That's also something which has worked quite well. But my research, my interaction, engagement with pre-service teachers who eventually become fully fledged teachers has been that the PhET simulation is something which works. It's something which is feasible. It is viable. It is low cost. It can be downloaded. Learners can engage with it at any time that is convenient to them. The PhET simulations are well designed. They are based on research which has been done. They focus on particular topics which are problematic topics, topics which are rich in misconceptions. So, I think teachers have a good appreciation of it, and they have been very effectively able to integrate these PhET simulations, in the teaching of various topics. And, the research which I have conducted certainly supports all of this. So I would certainly encourage, teachers to explore it. Often when there's innovation, it's something which is very much a stepped approach, taking the small steps, perhaps starting off by using PhET simulations as interactive demonstrations, playing it to the class, engaging your learners in a discussion on what they are observing, trying to facilitate a discussion where they explain what is it that they are able to observe. They are able to offer a scientific explanation to it. So that is the advice which I would give to teachers if they have not used PhET simulations before.
Great, thank you. And the second question is about like upskilling the teachers. So you've talked about competences that are addressed by the PhET simulations. So what upskilling of teachers would you recommend in terms of building their capacity on inquiry-based teaching and discovery learning uses resources like PhET simulations for STEM learning and teaching?
Yes, so, we often refer to the TPAC framework when it comes to integrating technology in education. So that's technological, pedagogical, content knowledge. So what it incorporates, one type of knowledge is the technological knowledge. I don't think the technological knowledge is going to be a challenge when it comes to PhET simulations because they are so user-friendly, right? The other form of knowledge is the pedagogical knowledge which teachers need to employ when it comes to utilizing PhET simulation. So they need to understand what's inquiry-based learning. Firstly, what is the purpose of inquiry-based learning? It is autonomous learning. It's about engaging learners on their conceptions, their understanding, which they already have, and to give them the opportunity to be able to investigate these ideas. So I think the PhET simulation is a great platform for that. So when it comes to teacher education, I think we need to focus on the technological knowledge. Many teachers, maybe are not confident enough with technology. I think some are also quite cynical about using technology in the classroom. So we've got to convince teachers on that. And secondly, one has to, focus on what is the appropriate pedagogical approach that can be used so that we are able to optimally utilize that technology. So I think these are two areas which one needs to focus on in teacher education. And certainly, we are addressing it in our own education programs, and no doubt, at other universities as well.
Great. We also have another question here. What would be the criteria for identifying which practicals are best done through simulations and which ones would work best being done in the lab?
Right. So I think that's a great question. I think firstly, one maybe needs to do a needs analysis of the resources which are available. As I said, if you do have sufficient resources, then I would certainly, suggest, a hybrid approach where you give learners the first-hand experiences of the physical, the wet laboratory, as we refer to it, as well as the PhET simulation. But from what I've seen, I think PhET simulations have been used quite extensively in chemistry, because the phenomena in chemistry happen at a submicroscopic level. So, you cannot perceive an atom, you cannot perceive a molecule. And it's a good way for the learners to understand the dynamic nature of chemistry. So, so I think firstly, it depends on what resources you have. Secondly, looking at perhaps a blended approach. There are topics in science, as I mentioned, where some common misconceptions are documented, and even learners doing physical experiments in a laboratory, it does not necessarily result in a conceptual change. But PhET simulation, as I have learned, is quite effective in bringing about this conceptual change. So, looking at topics where there are, rich misconceptions, as I said, many of these misconceptions, they are quite resistant to change because this is what learners believe in. They are quite comfortable with that, although it is scientifically flawed. So, maybe those could be some of the criteria which could inform, when is it that the teachers would use simulations.
Great, thank you. Maybe one last question before I take it back to Shola. This is a question from Rwanda, from Gerard, and he says, Dear Prof, what piece of advice may you give us about proper ways of preparing sim-based practical activities in order to maximize students' engagement in science class sessions?
So, I think as I said, one of the affordances of the PhET is the interactivity. So you got to plan so that the students are optimally engaged in the activity. I know it is not always possible that it can be a one-on-one engagement with a simulation. So you may have to plan activities, group activities, where you have maybe 3 or 4 learners who are at the same time engaged on the same simulation. And I think there are benefits to that because it affords itself now to peer learning. The learners are able to, interact on their ideas. What is it that they are experiencing? Discussions, healthy scientific engagements, supporting critical thinking. So, so I think for me, that would perhaps be the key takeaway, is that you need to plan for interactivity, you need to plan for learner engagement, but at the same time thinking about what is it what is going to be your role in this? You know, how would you be able to facilitate this discussion? And I think also after the PhET engagement, bringing the whole class together and for the learners to now share on their experiences of PhET simulation. So, you know, that is what I would suggest.
Great, thank you. There are many more questions in the chat, but we'll be able to follow up after this via email. And yeah, my key takeaway is that, you know, the simulations allow for more lab experiences, and two, the simulations also make it easy for every student to participate and, you know, like science. So I'll take it back to Shola to conclude. Shola, back to you.
Thank you so much, Zach. And we are already out of time. Just two things to say before we close. First is to appreciate Professor Umesh for such an insightful presentation, and also, of course, getting this conversation started. It is just the first of the series. So we encourage everyone to, of course, keep tabs and continue to join us every month. Third Wednesday of each month at around this time, we're going to be meeting again and addressing a lot of the concerns we have. So today's conversation perhaps was broad, but some of the things we've addressed about specific pedagogies and how to leverage tools, or how to also support teachers better, definitely will then be focused on at each of the session. I also encourage, if you check the chat now, the link to the Facebook group has been posted there. So please, I encourage everyone to join. So even before the conversation, of course, we can keep this going. We can connect as a community, learn from each other's experience, ask questions, and get the team, as well as other members of the larger community, to respond. I want to appreciate everyone again for joining us today, and look forward to future conversation, and I hope you will continue to join us. We're on the hour now, and it's sad that we have to go, but we have to respect everyone's time. So please join us again, and thank you for joining us. Goodbye for now.